After studying this module, you shall be able to know what are parametric and non-parametric tests, the concept of parametric tests and their applications, the concept of non-parametric tests and their applications, and differences between parametric and non-parametric tests. The statistical analysis of behavioral research data popularly employs parametric and non-parametric tests. The distinction between the tests is based on the assumption of population parameter and the type of data to be analyzed. The normalcy of the population of scores from which the sample is drawn is to be normally distributed for the parametric tests, but the non-parametric tests are not bound by this. The parametric tests are applied on data measured in quantitative scales of measurement. The non-parametric tests, on the other hand, are more suitable for the data in the qualitative scale. It is seen that the parametric statistical tests enjoy an edge over the non-parametric tests in the terms of power of a test, parametric ones being more powerful. However, it is important to meet the assumptions of the parametric tests for their optimal application to the data. The non-parametric tests, on the other hand, have limited scope and applications. Their use is found in the data that do not meet the assumptions of the parametric tests. In the present module, the reader will be explained the concept of the two major types of statistical tests, parametric and non-parametric, along with their applications. The numerical and theoretical concepts of various types of tests under each category will be taken up in the later modules. Let us have a look at the popular parametric tests, students t-test, z-test, f-test and Pearson's R, non-parametric test, chi-square, Wilcoxon Mann-Whitney U-test, Kendall's tau, Kruskal-Wallis. Of course, there are many more, but it is just an introduction to the readers for the limited types. The parametric test. The concept of parametric test. The name parametric test itself seems to draw from the fact that the tests depend heavily upon the parameters obtained and estimated from the data. The tests share two basic characteristics. The first characteristic being the assumption about the nature of parameters which have been taken on the selected variable. The second characteristic is the tests involve numeric calculations which require the estimation of the population parameters from the sample data. So, the population parameters and their estimation from sample is the key to the parametric tests. These tests are also referred to as the assumption based tests and are therefore should be used only when their requirements are met. However, there are aberrations in meeting the assumptions and still under some circumstances parametric tests are found to be suitable. Some of the most popularly used parametric tests are t-test, f-test, z-test, ANOVA, etc. etc. The numerical calculations and additional information about these tests is discussed in the succeeding modules. Let us discuss the assumptions on which the parametric tests are based. As stated before, these assumptions rely on the nature of the population distribution and the scale of measurement used for quantifying the variables. Assumptions of parametric test. The parametric tests are referred to as assumption based tests and they frequently require the following assumptions to be fulfilled before their implementation to the data. The data should be independent, that is, no observations drawn from the individual can be repeated. So, the selection of an individual to a sample is not dependent upon the selection of any other individual. The observations should be drawn from a population that has a normal distribution of the variable being quantified. So the observation should be extracted from only normally distributed populations. The samples drawn from a population must follow homogeneity of variance, that is, samples of a population should have approximately same variance. There should not be any significant difference in the variances of the samples drawn from a population. This assumption holds more strongly under the circumstances when the sample size is small. The variable being quantified must be in higher scales of measurement, that is, interval or ratio scales of measurement. The data in the qualitative scales, namely nominal and ordinal, is not suitable for parametric tests. The data should be continuous in nature to qualify for parametric tests. It should be kept in mind that the above discussed assumptions are the preliminary requirements for the parametric tests. Additional criteria do exist for certain tests under this class, and we shall take them up in the coming modules as we discuss the particular type of parametric test. One must also know that researchers do ignore some of these assumptions and therefore interfere with the validity of the study. It should be kept in mind that when the sample size is large, certain violations in the assumptions do not matter very much. The tests still enjoy considerable statistical power. The statisticians are also less concerned with the criteria of scale of measurement being used to quantify the variable. It is not wise to apply parametric tests to the nominal and ordinal data. However, if the data is an ordinal scale of measurement and has sufficient level, example 7 or more as in Likert scale, and other assumptions are met, one can consider applying parametric test, as stated by Tabachnik and Fidel in 2001. It is important to note that if the criteria of a parametric test are not met by the data, then it will be inappropriate to use the test. Although it should be kept in mind that such data would be suitable for non-parametric test applications as they have their own set of criteria taken care of. In spite of the violations of the assumptions, the parametric tests, they have been found to be reasonably accurate. But in certain conditions, the robustness of these tests can be badly affected. This may mislead the results and the probability of type 1 errors may markedly increase. Although there are statistical procedures that may indicate violations in the assumptions of parametric tests, they are themselves dependent on some hypothesis testing, on the same hypothesis testing procedures. So, similar problems associated with statistical power may crop up there too. It should be kept in mind that if a large sample is used, then even a small and unimportant degree of violation can be detected. Therefore, such tests that detect violations of assumptions should be employed to know how far the data is from ideal conditions of parametric applications. Level of significance. Statistical significance simply means that we are very sure that a statistic is reliable. It doesn't mean the finding is important or that it has any decision-making utility. The significance level is a critical probability associated with a statistical hypothesis test that indicates how likely it is that an inference supporting a difference between an observed value and some statistical expectation is true. Level of significance alpha is the probability value used as a criterion to decide that an obtained statistic has a low value of appearing by chance if the null hypothesis is true. The p-value stands for the probability value and is essentially another name for an observed or computed significance level. The probability in a p-value is that the statistical expectation null for a given test is true. So, low p-value means that there is little likelihood that the statistical expectation is true. This means the researcher's hypothesis suggesting a difference between an observed mean and the population mean, or between an observed frequency and a population frequency, or for a relationship between two variables, is likely supported. In psychological research, the level of significance generally used is 0.05 and 0.01. For example, suppose we give 1000 people an IQ test and we ask if there is a significant difference between scores of males and females. The mean scores for the male is 98 and the mean scores for the females is 100. We use an independent groups t-test and find that the difference is significant at the 0.001 level. Here, the t-test is significant because there was a large sample size. One-tailed and two-tailed test. One-tailed test or the directional tests. Here, the alternative hypothesis HA states that the parameter differs from the stated value of HO in one particular direction. The critical region is in one tail of the sampling distribution. The two-tailed test or the non-directional test. Here, the alternative hypothesis HA states that the parameter may be less or greater than the stated value of HO, or the null hypothesis, that is, the critical region is divided between both the tails of the sampling distribution. The image talks about the two-tailed versus one-tailed hypothesis tests. We can see how the region of acceptance and rejection are distributed for one-tailed and two-tailed hypothesis. The types of errors. Hypothesis testing using sample observations is based on probability theory. We make an observation of a sample and use it to infer the probability that some observations is true within the population and the sample represents. Because we cannot make any statement about a sample with complete certainty, there is always the chance that an error will be made. Decision errors. The researcher using sampling run the risk of committing two types of error. Decision errors are the situations in which the right procedures lead to the wrong decisions. There are two types of decision errors in hypothesis testing, referred to as type 1 and type 2 errors. Type 1 error. The type 1 error occurs when a condition that is true in the population is rejected based on our statistical observations. It is the incorrect rejection of a true null hypothesis that happens here. It is a false positive. Usually a type 1 error leads one to conclude that a supposed effect or relationship exists when in fact it does not exist. Example of type 1 errors include a test that shows a patient to have a disease when in fact the patient does not have the disease, or an experiment indicating that a medical treatment should cure a disease when in fact it does not cure. Type 2 error. A type 2 error, or the decision error of the second kind, is the failure to reject a false null hypothesis. It is a false negative. Example of type 2 errors would be a blood test failing to detect the disease when it was designed to detect it in a patient who really has the disease, or a clinical trial of a medical treatment failing to show that the treatment works when really it works. When comparing two means, concluding the means were different when in reality they were not different would be type 1 error. Concluding the means were not different when in reality they were different would be type 2 error. This two type of error are explained diagrammatically also, and we can see that when we fail to reject the null hypothesis and the null hypothesis is true, it is actually a correct decision. But if we fail to reject the null hypothesis, when the null hypothesis is false, then we commit a type 2 error or the beta error. It is called as the false negative. Rejecting the null hypothesis, when the null hypothesis is true, then we commit type 1 error, also called as the alpha error or the false positive. Whereas rejecting the null hypothesis when the null hypothesis is false is a correct decision and it leads to the right results. Remember that if the null hypothesis is true, it should not be rejected. But if the null hypothesis is false, it should be rejected. The problem is that you will not know if the null hypothesis is true or false. You only have the probabilistic evidence obtained from your sample data. Power of a test. Power is probability of rejecting the null hypothesis when it is truly false. Sometimes it is defined as the probability of correctly rejecting the null hypothesis. It is defined as 1 minus beta, 1 minus the probability of failing to reject a false null hypothesis. Remember, type 2 error, accept null hypothesis when it is in fact false. It is denoted by the symbol beta. The power is thus related to the size of both alpha and beta. The smaller the alpha value, the greater the beta value, and smaller the power, that is, smaller the probability of a type 1 error, the higher the probability of a type 2 error, and subsequently the smaller the power of a test. Thus, power is an easy idea in the statistical world. You want to correctly reject a false null hypothesis. Power is the probability of correctly rejecting a false null hypothesis. It means that the chance of finding what you are looking for. The non-parametric test. The concept of non-parametric test. When the data are in the qualitative scales of measurement, an application of parametric tests is not suggested. The non-parametric tests come to the researcher's rescue. The non-parametric tests are those statistical tests where there is no knowledge about the population and its parameters. Even in such situations, it is required and is essential to test the hypothesis about the population parameters. Non-parametric tests do not recommend any conditions about the population parameters, as they do not need compliance to distribution characteristics. The tests are thus called distribution-free tests. The non-parametric tests cater to the data that is obtained in the qualitative scales. The data is in the forms of either frequency counts or rankings. For the reason that the data is in lower scale, it is thought that non-parametric tests are low on precision and prone to type 2 error, that is, accepting the null hypothesis even when it is false. It is perhaps for this reason only that non-parametric tests are low on popularity and are used only when the data does not comply with the assumptions of parametric tests. However, statisticians do have counter arguments that as the non-parametric tests are not dependent upon assumptions, which are often flouted, for their validity they are more dependable. Some of the popularly used non-parametric tests are Mann-Whitney U test, rank sum test, Kruskal-Wallis test, Kendall's tau, etc., etc. Assumptions of non-parametric tests. These tests are also referred to as assumption-free tests, as they do not stress heavily on their conditional applications. Although the tests do expect certain characteristics to be fulfilled by the data, they are not rigid and elaborate. However, it does not mean that the tests are completely assumption-free. There are certain prerequisites associated with these tests too. Some of the requirements for the application of non-parametric tests are: the population from which the research samples are drawn may not be normal. The variables are measured in nominal scale, that is the frequency counts, or ordinal scale, that is the rankings, and the observations must be independent. The differences between parametric and non-parametric tests. After an understanding of the two broad categorization of the statistical tests, it is easier to differentiate between them. This differentiation is important in the light that their justified application to the data brings increased validity to the findings. Let us have a look at the points on which the parametric and the non-parametric tests differ with each other. Some of the differences between the two types have been illustrated in the table. The first column discusses the parametric test and the second column discusses the non-parametric test on certain qualities. The parametric tests are those statistical tests where information about the population is completely known by means and ways of its parameters. On the same continuum, non-parametric tests are those statistical tests where there is absolutely no knowledge about the population and parameters, but still it is required to test the hypothesis of the population. The parametric tests assume that the data comes from type of probability distribution, and then it makes inferences about the parameters of the distribution. The non-parametric tests, on the other hand, on similar dimension, cover the technique that do not rely on data belonging to any particular distribution. The parametric tests make more assumptions. If they are correct, the test can produce accurate estimates. Otherwise, the test could be misleading. The non-parametric tests, on the other hand, make few assumptions. Therefore, their applicability can be much wider. The parametric tests have more statistical power, which may be not as much in the case of non-parametric. The parametric tests are in the higher levels of measurement, whereas the qualitative scales or the lower levels of measurement are ascribed to non-parametric tests. The assumption of normality and the non-parametric tests are not complying to the normality assumption. No parametric tests exist for nominal scale data. The non-parametric tests exist for nominal and ordinal scale data both. We have already discussed the popular methods of parametric and non-parametric. Of course, there are many more methods, as we shall see in the succeeding sections, and of course, there are many more available in the statistics books. The advantages and disadvantages of non-parametric tests over parametric tests. Although the parametric tests enjoy greater popularity in the field of statistical applications, the non-parametric tests have their own utility and advantages. Let us compare the advantages and disadvantages of both in terms of derivations, applications, assumptions, and statistical power, ease of application and simplicity. As the non-parametric tests are concerned with data in basic scales, it is easier and simpler to apply them. The parametric tests, on the other hand, need mathematical knowledge and are difficult to comprehend by the researchers with no mathematical background. Simpler or no assumption compliance. The non-parametric tests in comparison to the parametric ones are based on fewer and flexible assumptions. As the compliance to a number of assumptions about the population parameters is not needed, the non-parametric tests enjoy wider scope of application. Violations in assumptions. The parametric tests have rigid assumptions and adhere to and thus are difficult to comply. These violated assumptions affect the validity of the results when the tests are used despite of assumptions. The non-parametric tests are less susceptible to violations, which if detected can be easily rectified also. But if all the assumptions of the parametric tests are fulfilled, they enjoy a clear edge over their non-parametric counterparts. Scales of measurement. The parametric tests with their higher level of measurement, interval and ratio use more enriched and profound data that is conducive to higher order statistical analysis. This presents refined, reliable and more powerful data analysis opportunities to the researchers. Sample size. One of the main factors used in the two tests is the size of the sample drawn to. The parametric tests with small sample size are a waste of data, as said by some statisticians. The non-parametric test, even with small sample size, even when it is less than 10, are efficient, easy to apply and prove better than parametric equivalence. So, whenever a researcher encounters data that is more suitable to parametric applications, they should be used. The non-parametric tests prove more powerful and efficient in other cases. Non-parametric tests are very simple and easy to comprehend. No assumption is made for parent population. Non-parametric tests does not involve complex sampling theories, and non-parametric tests are not as efficient as parametric tests. Non-parametric tests have less statistical power than their parametric counterparts. The other concepts that can be talked about and pertaining to parametric as well as non-parametric tests are discussed in the coming sections of the module. We summarize that parametric tests are those statistical tests in which the information about the population is completely known by means of ways of its parameters. Statistical significance simply means we are very sure that the statistic is reliable. It does not mean finding is important or that it has any decision making utility. In one-tailed test, HA states that the parametric differs from the stated value of HO only in one direction, whereas the two-tailed test it differs from HO in two directions. Decision errors are there. There are type 1 and type 2 errors, and they have been also discussed in the text. The non-parametric tests are those statistical tests where there is no knowledge about the population parameters but still is required and is essential to test the hypothesis of population. Some of the popular examples are Mann-Whitney test, rank sum test, Kruskal-Wallis test, and of course there are many more. Parametric tests have a normality assumption. Non-parametric tests have no normality assumption. Parametric tests make more assumptions while non-parametric tests make less assumptions.